This didactic material is meant for the personal use of the student only and is copyrighted. Its reproduction, even for a partial utilization, is strictly forbidden in compliance with and in force of the law on the author's rights.
Hello, this is the third lecture in mathematics of the International Master in Business and Administration, and today we will introduce the following topics. As you can see, economic applications, rank of a matrix, and differential calculus, the first part. These are the topics. Just to repeat, economic applications, rank of a matrix, and differential calculus. First part, the second part on the fourth lecture. And the aims of the lessons are knowing how to apply matrix algebra to the economics problem, applying Cramer's rule to some economics application or problem, knowing the basics of differential calculus and its fundamental theorems. We saw in the last lecture the linear two-market model. And now we want to formalize this situation we have here. As you can see, the problem is the following. Matrix A times X equal P. Now, matrix A is this one. The variables that we want to compute, P1, P2, are the X, and then the parameters are B0 minus A0 and beta 0 minus alpha 0. And what we want to do is to compute P1 and P2. And we want to use Cramer's rule. And this is a very simple application to this problem, the two-market model. Then we want something important. We pretend if we want to evaluate P1 and P2, the determinant of the matrix A with the elements A1 minus B1, A2 minus B2, alpha 1 minus beta 1 and alpha 2 minus beta 2 must not 0 or different from 0. Then P1 is very easy to compute and P2 too. With Cramer's rule, we take this element and substitute on the first column, and this term want to substitute to the second column, and the quotient is, this is the determinant of matrix A, and this is the determinant of matrix A, and this must be obviously different from 0. And with Cramer's rule, we compute easy P1 and P2. This is a very simple application, as you can see. Then we have a three variables problem, but it's the same. The matrix A times X then is equal B. And this time the matrix A has these elements. The column of variable is this one, and the column of parameters is B. And determinant of A must not 0 if we want to compute C, I, and Y. Capital C, capital I, capital Y. Then it's the same as before. We just substitute the first column, the column of the parameters in the first one to evaluate C, then on the second column to evaluate I, and to the third column to evaluate y. And this is always Cramer. And this is always using Cramer's rule. These are all very, very easy calculation. The determinant of all these metrics we can calculate with Sarro's rule or using the multiplication between the first element and the minor, the first element and the minor, the first element and the minor, and for the second is the same, for the third is the same, only we just to remember that when we want to compute the minor here, we have to change sign. As you can see, it's very easy to do that. And this is another income determination model with three variables, C, capital I, and capital Y. Then we want to use algebra to determine the ISLM model. This is investment savings, liquidity and money supply, liquidity, preference and money supply. In the income determination model, we regard interest rate as given and consider only the product market. Now we enlarge the model to include the money market and regard the interest rate as the price, an endogenous variable determined in the money market. So we can build a table with 3 elements on the row and 2 elements on the column. The good market column and the money market column. In the good market column, the 3 rows are: the consumption is equal to A plus B times Y. Everything is capital and okay. And I is equal I0 minus I times R, the interest rate, and C plus I plus G over market equal W. This is the good market. We have 3 equations. And the other column we have the money market and first row L. The liquidity preference is equal to K times Y minus L times R, and M equal M over market with the equilibrium condition M equal L. Then the endogenous variable are CIY interest rate, L the demand for money, and M the money supply. Now we want to, we can summarize the model with the following graph. The straight line with negative slope are the IS1, IS2 in 2 different points, Y1 and this one, Y2 and these 2, crossing the LM straight line with positive slope. Then okay, we have the exogenous variable too, equal to capital G over market, capital M over market. These are the quantity of money, and all the parameters A, B, I, K, L. We want now to substitute into the equilibrium conditions. Then we have the good market. This is the equation for the good market. Then the money market. Then we have this equation. And then the endogenous variable that we want to compute, capital Y and capital R, the income and the interest rate. Now we want to build the matrix of the coefficients of the capital Y and capital R. And this is the matrix. With straightforward calculation, you build the matrix very easy. This is our A matrix, this one. These are the column of the variable X example. And this is the matrix B. Always we want to build this equation. A times x equal b, and we want to compute x, and we know that x is easy to compute if the inverse of matrix, I'm sorry, this is b. Okay. Then we pretend that this determinant must not 0. This is not 0. And then we build, using Cramer's rule, this situation here, the quotient. Then we substitute this element on the first column to evaluate y. This is the first variable. And then we substitute in the second column to evaluate the second variable using Cramer. Okay. These are all coefficients, and calculation are very, very easy. It's not very hard to check that y and r, if determinants of A is different from 0, we have just a solution, then we can calculate y and r directly. Then we can do this another model, two-country income determination model. Another extension of the income determination model is to consider the interaction between domestic country and the rest of the world. This we call foreign country. Domestic good country, foreign good market, and endogenous variable are the elements that are building this table. And then we want to use, again, matrix algebra, determinants, Cramer's rule, to evaluate our variable. These are all the equations. First equation for domestic good market to evaluate capital C. Then the second equation, third equation, fourth equation. For foreign good market, we are different parameters. In the first one, we have A, B, then we have here A prime, B prime. In the equilibrium model here is capital I equal capital I0, then we have capital I prime equal capital I prime 0, and then for the other, M is the import and X is the export. The endogenous variable are C, I, Y, capital OK, capital C prime, capital I prime, capital Y prime, capital M prime, and capital X prime. Then we, by the definition, these are the condition for the equilibrium. Then we substitute into the equilibrium conditions. Then we got this chain of equation. This 1 minus B plus M in parentheses times Y minus M prime times Y prime equal A0 plus I0 plus M prime 0 minus M0 times M0. This is a function 1 minus B prime plus M prime Y prime minus this element equalized to this one. And then we want to build a simple matrix. This is the matrix, always the matrix A, with all the coefficients of our variables. In this case, the variable are Y and Y prime. For the domestic good market, Y, capital Y, and for the foreign good market, capital Y prime. These are the coefficients. Then we want to use always, we use matrix determinant and Cramer's rule to evaluate capital Y prime. These are, the method is always the same. For the first variable, we substitute in the first column and we take the column here fixed. Then for the second variable we substitute the second column and we take here the element fixed. And this is the determinant of this is the determinant of matrix A that must be different from 0. And these are always very easy calculation. Then we have an input-output table. This is our assumption. Technologies are all fixed proportional. That is, to produce 1 unit of product capital Xi, you need Aij units of X, capital Xj. Then we have this matrix A with all these elements. This is a very easy n by n matrix, n by n matrix, n by n matrix is a square matrix, A11, A12, A1, and A21, A22, A2, and till AN1, AN2, ANN. Column E represents the coefficients of inputs needed to produce 1 unit of capital Xi. Somewhere here there is a column E with A1E, A1E, A2E, ANE. Suppose we want to produce a list of outputs. These are our outputs. Is a column vector x1, x2, xn. Then we need a list of inputs. And these are our elements of the equation. A times x. This x multiplied for all the elements of the matrix A. As you can see, A11 times x1, A plus A12 times x2 plus 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 A1n times xn, and then to the nth row of an1 times x1 plus an2 times x2 plus 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 ann times xn. That output is x minus a times x. Then we can write here I minus a in parentheses times x. If we want to produce a net amount of v, this element here has a column. These are our parameters here. Then we build this equation. D must be equal capital I minus a in parentheses times x, and then, of course, then x must be equal I minus a in parentheses the inverse times d. Then we need that this element must be different from 0 if you want to calculate x. Then we have a geometric interpretation of determinants. Because of properties 2 and 4, the determinant function dv1vn, v1vn is a collection vector. It's called an alternative linear n form of the n-dimensional space R. It's equal to the volume of the parallel pipe formed by the vectors v1, vn. And for n equal to the determinant, this is a property of determinant. The property is the area of the parallelogram formed by the column vector a11, a12, a21, a22, and you can see in the diagram this is the determinant, this area. In 3 dimensions is a volume. N equal 3, then determinant of matrix A is equal volume. In 3-dimensional space is a volume. And these are properties of determinants. Okay. If the determinant is 0, then the volume is 0. And the vectors are linearly dependent. Always remember this property, linearly dependent. One of them must be a linear combination of the others. Therefore, an inverse mapping does not exist, because we have seen that the inverse in this case does not exist, and A is a singular matrix. Now, 3, we want to see that the rank of a matrix as a solution of this equation, A times X equals D, when this time the determinant of A is equal to 0. We want to remember that rank of A is the maximum number of independent vectors in A, which is formed by all the vector v1, vn. And this is the dimension of range space of all linear transformation of the matrix. Remember that we can, in a matrix, do the linear transformation. And then if we have some linearly dependent vectors, we can remove, and which remains is the number of the independent vector. And the rank of A is equal to the size of the largest non-singular square submatrices of A. And this is an example. 1, 2, 3, 4, rank of this matrix is the matrix A. The rank of A is equal to. Why? Because the determinant of this matrix is equal, it's different from 0. Then it's 1 times 4, 4, minus 3 times 2 is equal, in this case, minus 2. Then we want to compute, or want to see, which is the rank of the matrix A, in this case 1, 2, 3, 4, 5, 6, 7, 8, 9. It's easy to check that the determinant of this matrix is equal to 0. And the meaning why one of these column or row is a linear combination of the other two. And then the rank is 2, because if I take this minor, 1, 2, 4, 5, I take this minor here. This is a submatrix of A. I want to call B. B is in A, and the determinant of B is not 0, and that's meaning rank of matrix B is equal to, is not singular, because the determinant is different from 0. Then we have some properties. Property 1, the rank of A times B is always smaller than or equal to the minimum of this set, rank of A or rank of B. If rank of A is 2 and the rank of B is 3, then rank of A times B is equal to, and this is the minimum value that I can take from rank of A and rank of B. Property 2, the dimension of a null space of all linear transformation of A plus the dimension of range space of all linear transformation is obviously equal n. If we have a matrix n by n matrix, and we have some dimension here of the null space where the linear transformation, the linear mapping are 0 somewhere, plus this dimension, then we got all the dimensions equal n. Consider the simultaneous equation A times X equal D. When the determinant is 0, there exists a row of A that is a linear combination of other rows. And we have to always to figure that the rows are the equation, the number of rows are the number of equations of a linear system, and the number of the columns are the variable. Here we have the number of equations, and here we have the number of variable. Then, if there is a row of A that is a linear combination of other rows, and the rank of A is smaller than n, first we have to form the augmented matrix M, capital M. This is the matrix A, and with the D vectors, and calculate the rank of M. Then we have two possible cases. Case 1, rank of M is equal to rank of A. In this case, some equations are linear combination of others. Then the equations are dependent and can be removed without changing the solution space. We can do this operation. We can do. There will be more variables than equations after removing these equations. Hence, there will be an infinite number of solutions. If we take away, if we remove one variable, then one equation, then we have infinity with order 1 solution. Or if we remove two equation, then we have infinite with order 2 till it's possible to reach order n minus k, the number of the equation we can remove. And if n is equal k, then we have infinite to the 0, then is 1, then we have infinite, 0 is 1, then we have write the solution. This is the reason why we can always remove without changing if the equations are dependent. Then we have this situation. This is a very easy example. 1, 2, 2, 4. This is our matrix A, and these are our variable. These are our parameters. Then the rank of A is equal the rank of a matrix 1, 2, 2, 4, and this is a rank is equal 1. Why? 1, 2, if we multiply the first row with 2, 2, 1, 2, 2, 4, we obtain 2, 4, 2, 4. And this is the reason why the rank of matrix is 1. And this is equal to rank of the augmented matrix M, as you can easily check. Then the second equation is just twice, as we can see, the first equation, and can be discarded. Then the solution are x1 is 3 minus 2k, and x2 is equal k. I can choose x like a scalar number in R, and x1 depend on the choice of k. A k can be whatever I want. And the geometric meaning of this situation is on the x1, x2 space, the two equations are represented by the same line, and every point on the line is a solution. The solution is on the line, on this straight line. This is the situation here. The reason why is x1, x2, and every point is on this straight line. Case 2, rank of the augmented matrix is equal to rank of A plus 1. In this case, there exists an equation whose left-hand side is a linear combination of the left-hand side of the other equations, but whose right-hand side is different from the same linear combination of the right-hand side of the other equations. Therefore, the equation system is contradictory and there will be no solutions. As we can see here, example 1, 2, 2, 4 as before. Then we have our variable x1, x2, that is, must be equal 3 and 7. But if multiply the first equation by 2, then we have 2, 4, 2, 4, x1, x2 equal 6 and 7. It is impossible. The rank of A is 1, but rank of the augmented matrix is 2. Then it's impossible to have a solution, because rank of A is smaller than rank of the augmented matrix. Multiplying the first equation by 2, as I said before, 2 times x1 plus 4 times x2 is equals 6, whereas the second equation says 2 times x1 plus 4 times x2 is equal 7. Therefore, it's impossible to have a solution. No? This vector is a solution vector, satisfying both equations simultaneously. It's impossible. On x1, x2 space, the two equations are represented by two parallel lines and cannot have any intersection point. Because, as we know, this is the equation of a line, and this is an equation of a different line. If I can plot this situation is like before. This is the first one, and this is the second one. These are parallel. This is the first one, R1, R2. And this is the reason why it's impossible to have a solution of this problem. Because rank of A smaller than rank of M. And these are the two cases that we can see in this situation. Now we want to introduce differential calculus, because some model it's impossible to solve with matrix algebra. We need differential calculus. We need other mathematics objects or tools. As seen in the last chapter, a linear economic model can be represented by a matrix equation A times X equal the function of y, y, and solve using Cramer's rule. As we can see, X equal the inverse of matrix A times d of y. On the other hand, a closed form solution X equal X of y, as X, we can see X as a function of the other variable y for a nonlinear economic model is in most applications impossible to obtain. For general nonlinear economic models, we use differential calculus, implicit function theorem, for example, to obtain the derivatives of the endogenous variables with respect to exogenous variables. These are the symbol. We want to compute the derivative of xi with respect to yj. Then we can build this system of function. First function in x1, xn, endogenous variable, y1, ym, exogenous variable, till fn, x1, xn, y1, ym, and we pretend are all 0 in a nonlinear economic model. This is our constraint in a nonlinear economic model. Then we build matrix, but this time we want to build a derivative matrix, and then we have to first introduce the meaning of all this symbol. The first matrix is the matrix of all the derivative function with respect to all the x and variables. The second matrix, the second matrix is the partial derivative of the x1, xn function with respect to the y1, ym. We want to obtain the derivatives of the endogenous variables with respect to the exogenous variables. Then we build the function, then we build a system of matrices, and we want to compute minus the derivative function of with respect with all the exogenous variables. Then we can do a simple multiplication here, but this matrix must be not equal 0, otherwise we have no possibility to do anything, no possibility. And we want to compute this matrix, the matrix of all partial derivative of xi with respect to the yj. The xi goes from 1 to n, and the y goes to 1 to m. Okay. Each of this derivative represents a cause-effect relationship. Okay, this is very important. And if the partial derivative of the xi with respect to yj is bigger than 0 or smaller than 0, then xi will increase or decrease when yj increases. Therefore, instead of computing xi as a function of y, we want to determine the sign of each derivative, the sign for each ij pair. In the following we will explain how it works, the sign, because as we will see, the derivative is a geometric very important meaning. And this is the fundamental of differential calculus. If I have a function x, the variable x is a function of variable y, I can always build, if this function is continuous and this limit exists, then I can build the derivative of f of y star, and this is dx, derivative of x with respect to y, every time y is equal y star. And this is the limit of delta y approaches to 0, then we have to build this quotient, and then we have f of y star plus delta y minus f y star over delta y. On epsilon x space, x as a function of y is represented by a curve, and f prime of y star represents the slope of the tangent line of the curve at the point yx equal to y star f of y star. This is the definition. This is the definition. Geometric definition and algebraic definition. This is algebraic and this is geometric definition of the derivative of a function. Then we have rules, derivative rules you can do by yourself, maybe the most important product, the quotient, then the exponential, then the sinus and cosinus, natural logarithms, and these are the most used in differential calculus. This is a table, very easy to understand. Is also important. Derivative of y to the n. First derivative is n times y to the n minus 1, or the derivative of a constant. If x is constant, then the first derivative is always 0. Okay. Then we can interpret the derivative of a function, and we have to do the following. When h approaches to 0, the point q, this point, q approaches point p, here. At this time, the second line, this one, the second line, as you can see, begins to resemble the tangent to the function f of y at the point P. And thus the angle alpha tends to be beta. The angle alpha tends to be beta. This is the geometric interpretation of the derivative of a function as Leibniz and Newton made. Then we can build the tangent of beta equal to the limit h approaches to 0 delta x over h, and this is the derivative in point A, right here. This is our function. In this point, except in this point, the function and the straight line, right in this small interval, are the same. They have the same behavior. Then we can see if beta is bigger than 0, then the curve in this interval, the slope is positive and the curve is increasing. If beta is smaller than 0, then we have the opposite situation. This is beta, and the function is decreasing in this interval. If beta is equal 0, it's possible to have a minimum or a maximum for our function. And this is the interpretation of the derivative of a function. We can see our curve as a straight line with the angle beta. And the straight line is tangent in point A. This tangent has the same behavior of the curve in this small infinitesimal interval. The slope of the tangent to the curve at the point, at the A point, is equal to the derivative of the function at the point mt equal the first derivative of A, f of A. Then we have I-order derivatives. If our function and the derivative is continuously, we can build f double prime of y. This is the derivative of this first derivative with respect dy. This is the second derivative with respect to y squared of our function f of y, and so on. We can build the f triple prime, the third derivative of derivative. As you can see, I can put the derivative and make derivation another time. And this is the third derivative with respect to y of our function f of y. Then we can build the partial derivatives. Why? In many cases, because in many cases x is a function of several y's, then we have to speak of partial derivatives. X is a function of y1 till yn different variable. The partial derivative of x with respect to y evaluated at y1, y2, yn is equal y1 star, y2 star, yn star. And then we can always build the definition. This is the definition. Partial derivative of x with respect to the ith variable must be, if there exists, the limit of delta ye approaches to 0. Then I have to make this fy 1 star y star plus the incremental of yi till yn star minus, this is our function, over the incremental of the variable delta yi. It's the same definition as before. This is n-dimensional, and this is the first was one-dimensional. That is, we regard all other independent variables as a constant. F as a function of yi only. I have to compute only the derivative of yi and do 1 time, 2 times, n times till n. For example, if I want to compute the partial derivative of the first variable to the n, and is times x, the second variable, to m with respect to first, this is using the basic rule, derivative basic rule, I can easily calculate n times x1 to the n minus 1, and the x, the second variable, remains the same. Will be no touch. And then I can build always the partial derivative with respect the second variable, and this is equal x1 times m times x2 to the m minus 1. High order derivatives. We can define high order derivatives. As before, for the case with two independent variables, there are 4 second order derivatives. This is the first one, the second one, third one, and the fourth. As you can see, the first one is the second derivative x with respect to the first variable squared. Then is the second derivative of x with respect of y2 with respect to y1. Then the second derivative, this time we have to change the order of variable, and the fourth one is the second derivative of x with respect to the second variable squared. First variable, second variable, then the second times the first times the second partial derivative. The notation are f1, f2, f11, this one, f12, this one, f21, this one, f22, this one. And these are very easy notation. We can write now an important element that we call the gradient vector of f. The gradient vector of f is a column vector formed by all the derivative, the first derivative of our function f1 till fn. And the second order derivative matrix is called Hessian matrix of f. This is symbol f11 till f1n, then fn1 till fnn. And then we can read the equality of cross derivatives. This is the Schwarz theorem. If f is twice continuously differentiable, then Fij must be equal, and if equal, Fji, and the Hf is symmetric. Symmetric. The matrix will be symmetric. The economic concept, similar to derivatives, then we can always define the elasticity of xi with respect to yj. This is the definition of elasticity. This is yj over xi times the derivative xi with respect to yj. The percentage change of xi when yj increases by 1%. And this is a very easy, simple QD equal the demand function with respect P. This is the elasticity. Very easy to check. Then we have the basic rule for the elasticity. Ex1, x2, y equal Ex1, y plus Ex2, y. Then this is product, this is the quotient, and this is the inverse. This is the growth rate per unit time, as very easy formula. 1 over x, partial derivative of x with respect t, derivative of x, the percentage change of x per unit of time. These are very easy. Then we want to introduce some very important theorems in differential calculus. The continuity theorem, the role theorem, and the mean value theorem, or Lagrange. The continuity theorem is f of y is continuous on the interval, the closed interval, AB, and f of a smaller than 0, f of b is greater than 0, greater or equal. Then there exists a point C in the interval AB such that FC is equal 0. Then we can see the interpretation, geometric interpretation. Rolle's theorem. If f of y is continuous on the interval, closed interval, AB, and f of a equal f of b equals 0, then there exists a point C such that the first derivative of the function in this point, at this point C, is equal to 0. Then the main value theorem. If f of y is continuously differentiable on the closed interval AB, then there exists a point C in the open interval AB such that we can write this f of b minus f of a is equal f prime of c, the first derivative at the point C multiplied by b minus a in parentheses. And this is the same. We can write the first derivative of c like the quotient between f of b minus f of a over b minus a. Then we can use also this theorem, Taylor's theorem, if f of y is k plus 1 times continuous differentiable, k plus 1 times continuous differentiable. The meaning is that I can build the first derivative, the second, the third, till the k derivative of the function and the k plus 1 derivative exists. I can always write a function as a sum of elements, and this becomes a polynomial. This becomes a polynomial. It's a differentiable on the closed interval AB. Then for each y in AB there exists a point C in the open interval AB. This is a B, not y. This is a B, such that f of y is a sum. This is a summation of f of a, the first derivative in a, y minus a plus the second derivative of a, y minus a squared over the factorial of 2 till the kth derivative of a over factorials of k, y minus a to the k in parentheses, and then I can build the k plus 1 derivative of f at the point C over k plus 1 factorial in parentheses, obviously, y minus a to the k plus 1. I can always arrange some function as sinus, cosinus, exponential, natural logarithms. I can always write a function like this as sum of this element and write a summation. A summation. Okay, we want to conclude our lesson with this geometric interpretation of Rolle's and Lagrange's theorem. The geometric interpretation of the mean value theorem tells us that there is a point where the tangent is parallel to the secant. The figure on the right. This is the mean value theorem here. On the right. This is the geometric interpretation. I can always find the point C, where the tangent line is parallel to the secant line through B and A. And Rolle's theorem is a special case of the mean value theorem. As you can see, this is the secant line between B and A. This is the maximum in this case at the point C in the open interval A, B, and these two straight lines are parallel. Okay, now we want to conclude the end of the lesson. The student knows the ISLM model and its principal applications, and knows Rolle's, Lagrange's, and Taylor theorem and their applications. Thank you very much for your attention. See you at the next lecture. Thank you very much. Bye-bye.